is a practical business problem using calculus. So it's about marginal revenue. And just so that we're clear, revenue is different from profit. Profit is revenue minus expenses. Revenue is just the money that you're taking in when you're selling something. So it's telling us that the revenue in dollars from selling X number of custom-made desks is represented by this equation. And the first question says they want us to graph it and find out, well, what values of X make sense in this problem situation. So I actually did graph this over here on Desmos. And this is what I got. And it looks very odd. It looks like a vertical line. But think about the equation before you start to freak out. This equation is, you can see up here, it's 2,000. I'm kind of circling it with my little cursor there. 2,000 times 1. So this equation is going to have a y-intercept of 2,000. So I better zoom out on this quite a bit to see what this thing's really going to look like. I need to zoom out until I get to where I can see 2,000. And now I can see what's happening with this graph. It's going up very steeply. I can't really tell my x values that well. But at 2,000, I have kind of a curve there. So what I did right now is I changed my settings on the graph so that I could see in my x-axis in steps of 1 instead of steps of 500 or 1,000 or whatever it was. And I could begin to get more of a shape out of this graph. Well, the question was asking, what values of x make sense in this problem situation? Well, the values of x that make sense are only going to be the positive numbers. I can't manufacture negative desks, so really this is what I call a first quadrant problem. All the action is happening in the first quadrant. The next question asks me to find the marginal revenue when X desks are sold. So marginal is a concept that deals with rate of change. What it's saying is that if I make one more desk, sorry for the pause there, Smartboard's acting up. What is going to be my increase in, or my decrease in revenue? What is going to be the rate of change in my revenue? So marginal is basically referring to delta y over delta x, which we know is represented by the derivative of the function at a particular point x. So let's calculate the derivative. Well, I think I'm going to change this into 2,000 minus 2,000 over x plus 1. So my r of x is equal to that. I just distributed my 2,000 like that. And I know if I want to do r prime, well, I know this 2,000 is going to go to 0. So I'm really just going to be left with this piece right here. And I'll set that up using the quotient rule. So uv minus uv over v squared, and there's my little prime there. So my derivative of 2,000 is 0, so I have 0 times x plus 1 minus, well, the derivative of v here is actually 1 times 2,000, and that's all divided by x plus 1 squared. So my r prime of x is equal to negative 2,000 over x plus 1 squared. But I made a mistake, because what I found here is the derivative of this, but there's a negative sign in front of it. So really it's negative, negative, so r prime of x is actually equal to 2,000 over x plus 1 squared. It's not negative 2,000. So the next question is asking, use the function r prime of x to estimate the increase in revenue that result from increasing sales from 5 desks a week to 6 desks per week. So really what that is asking is, what is the marginal revenue at 5 desks per week? So when I make 5, I want to know when my next increment of x goes up, what's going to be my revenue? So I'm going to go r prime of 5 is equal to 2,000 over 5 plus 1 squared. So 2,000 divided by 36. 2,000 divided by 36. Well, my revenue should go up approximately 55.56. That should be my increase in revenue from my 5th to my 6th desk. So the last question asks us to write something. It says, find the limit of r prime as x approaches infinity, and then how would I interpret this number? Well, okay, we can find the limit of this. So if we go back to our limits thinking, I want to find the limit as x approaches infinity of 2,000 over x plus 1 squared, which is going to be the same as the limit as x approaches infinity of 2,000 divided by the limit as x approaches infinity of x plus 1 squared. So this is the limit as x approaches infinity of 2,000 is just still 2,000. But this is divided by, well, infinity, because as x approaches infinity, this is going to get humongously large. So this is going to approach 0. Well, what's that telling me? Well, one thing it's telling me is that if I look at the graph that I designed here, it's saying that as x approaches infinity, as x gets really large, the slope is going to be getting closer and closer to 0. Well, let's see if we can make that look, if we can see what that looks like. So here I changed my x scale to go up to 100, and yes, I can see that the slope is getting flatter and flatter and flatter, and it's really approaching the number 2,000. Since this is the graph of my function, it is not the graph of the derivative, but what it's showing me is that my slope is approaching 0, my rate of change is getting really flat because my slope is getting close to 0. So what this is telling me is that as I produce more and more desks, each individual desk is going to account for less and less of an increase in revenue. And just for the fun of it right here, I just added the derivative of my function r, so you can kind of see that my marginal revenue really declines quite rapidly up until like about 10 desks or so, and then it just is very, very, very close to 0. It's hardly anything at all. So yeah, in fact, it even says it's 0, but I think it's some minute number. So making more and more of these custom desks really isn't going to increase my revenue by very much at all.